I want to thank Professor Kropkin and his team for inviting me and for inviting me to give this talk. So this talk is actually motivated by a paper which Professor Machenko sent me a few years ago. I haven't done much about it until recently. So I'm not actually going to model the iceberg, but I'm going to model the ship, which is to the right here, which is an image of FRAM. It's the historical dead water of Nansen. And the important point is the connection between now what happened to this ship in the dead water and this iceberg. So that's the story. That's the contents of my talk. So I've 8 points. I will start with the motivation, which is the observations of the drift of an iceberg in the Antarctica, and discuss what the authors of that paper discussed about the potential effect of internal waves. That is continued in part 2 or in point 2, and then I switch to the case with the historical dead water of Nansen. This is really the origin of the dead water, and because the connection is really spot on. So that is the point. So some of you have heard me speak about that, but I have some new computations which adds to what I did a few years ago. And then when I discuss the dead water on FRAM, you can do it 2 ways. You can do it actually from the direct observations, and then I compute it, and then you have actually an intersection between 2 different curves, so you can actually fix the speed of the ship. And then you can discuss what Nansen did not measure, which was a stratification. So if you have a stratification such and such, you get this and this and so on. So that fills into his observations. It would have been interesting to give this talk in front of him. So then, of course, it's strongly non-linear interfacial model calculations. And then I compute the wakes. How does a wake look like? And then I connect to the iceberg case. So all this happens at very low fluid number. So, of course, we have in the audience Professor Tuvia Milo, who has done a lot of dead water investigations, but that is for much larger fluid numbers. So I refer to all his work in the end. So then the iceberg case. This is a paper which Alexei sent me a few years ago, so you can read that. And they actually, and I think Mike showed an image of that iceberg in his talk this morning. So here you can see that they actually track. They have, so this is like one of the figures. They have a ship following this iceberg, the drift of it. And they measure the wind, they measure how the ice is piling up on the different sides of the iceberg, and they measure the iceberg velocity, which is very tiny. It's 14 centimeters per second. So here is the iceberg. It's quite impressive geometry, very big. What is the connection to FRAM? Well, you will see. Now we are getting to the point of the internal waves, because they actually measured some parts of the internal waves which are very, very interesting. So they measured the pycnocline level ahead of the iceberg and behind. And they found that actually the amplitude or the wave height of this internal wave elevation, actually, because it's not a wave here, it's like a local elevation, is comparable to the upper layer or the pycnocline level. So it's a very strong effect, actually. And then they also measured the pycnocline in the sea, some distance away from the iceberg, so you can kind of have a clear reference. And look to that jump. the relative jump is 0.05 per mil. It's very tiny. It's 10 to the minus 5. And still you can have this effect. And now we can, because now we can calculate now the reference speed of the internal waves. And then you have another key, that is a Frid number. So with this tiny jump in the density, you have a Frid number of 0.6, which is the drift velocity of the iceberg. And you have that the wave height is comparable to the upper layer depth, which is indicated here. So in this paper they have two measures, but I trust the measure which I did so far some distance away. Okay, so now I'm going to leave this iceberg. I'm going to discuss the historical observations of Nansen and model that. But okay, we are left with some questions here. First, how to quantify the internal wave drag, or how to quantify the strong increase of the internal wave drag at small subcritical speed, because the speed is really very small. So my angle of attack is to discuss an analogy with the iceberg and actually Fridtjof Nansen's original descriptions of the dead water, which you can read in his book. This is very old stuff, and in Ekman in 1905. But if you read those texts carefully, you have some, I mean, the original description is cleaner than the second one, because then they have some dopes where the measurements accurate and so on. So I discussed that in a paper, recent paper in a book from Morozov. But what Nansen actually wrote in his first book, or in his book, was that our speed was reduced to about a fifth part of what it would have otherwise have been. And then he discussed how was the internal wave field looking like from a ship, but the speed reduction is the important point here. And when you add the observations they included in now the famous paper by Ekman in 1904, they discuss if the speed of FRAM was 4.5 knots or 5 knots. But they add that the salt water at the level of the bottom cock at 4 meter depth was the water was salt. So it was intersecting with the pycnocline for sure. But they didn't measure the pycnocline. There is a very important information here. The engine was working at full pressure without and with the dead water. So actually with the informations 1, 2 and 3 we can calculate the dead water resistance on FRAM. So we need to define the internal wave reference speed. I'm using 2-layer model. In other papers we can do the same thing with 3-layer model. So this is linear, it's a long wave speed, and if I now use the conditions where Nansen was doing his observations and an upper depth layer of 4 meters, I have a reference speed of 1.02 meters per second. So then if you have different depths, of course you get different reference speeds. So here is FRAM, is a model of FRAM. So it has a length of 30 meters, beam 11 meters, and a draft of 5 meters. So then, of course, it was intersecting with the pycnocline. So the empirical calculations of the dead water resistance. So the mean work is simply balancing the frictional drag loss. And we know the speed. We can measure the wetted surface area, and here is a skin frictional resistance coefficient, and here is the density. And then we can do the same thing because the work is the same and with dead water. So then with dead water, of course, the speed has significantly reduced. So you get a resistance coefficient at a smaller Reynolds number, and then in addition you get this dead water resistance coefficient, which is a function of the fluid number. So then actually you can estimate the dead water resistance. So it's going by this ratio to the third power, and when you can estimate this from, this is done as a standard thing in the ship hydrodynamics, then you have a quite robust estimate of this skin frictional coefficient. So then you can calculate that the dead water resistance is 0.3. So with the speed reduction of 1 to 1/5. So that is 100 times bigger than the frictional resistance. So it's a tremendous effect. So now I work with the dead water resistance divided by this draft of FRAM over the mid-level of the pycnocline. That is an interesting quantity. And then we can plot this as function of the speed in the dead water as function of the fluid number. So if now the speed without dead water was 4 knots, you have this curve, and if it was 4.5 knots, you have this curve. And now the point is to calculate the same thing with theory, and then you have actually an interesting intersection here, and then you can start to discuss what was going on. So now it's a model. So this is potential theory. Of course, I can't do any braking. I can't do any intersection of the geometry with the pycnocline. I have an upper layer here. This is a free surface, which is a rigid lid. And I have y equal to 0 at the mid-level of the pycnocline. So this is now the upper layer. This is the free surface, yes, I said. The geometry, which is indicated here, has a function delta of xt and moves with a speed u. The interface has an elevation, function of x and time, or space and time. And then I have density rho 0 in the upper layer, rho 1 in the lower layer, and potential phi naught in the upper layer, potential phi 1 in the lower layer. This is under action of gravity, and I have a horizontal bottom. So everything is now a function of the fluid number, and because everything is scaled by all velocities are scaled by the linear long wave speed given here. So then I work with the potential at the surface, no velocity at the geometry, no velocities at both sides of the pycnocline, and the potentials at both sides of the pycnocline, and the jump and the sum. So this is now plugged into the kinematic and dynamic boundary conditions, which are fully nonlinear. And everything is done in the Fourier space. And then I do expansions of these normal velocities so that I just find all the potentials, where now all are obtained by use of integral equations, where the green functions are expanded in this delta and this eta. But it has a very interesting convergence. So it's a rapid method. I need two terms, and then for a quite big range, I'm quite okay. So I have some documentation on that, on the convergence. You can read all this. So everything is explicit. So then, of course, I need a force. That's the interesting part. So that is all terms included. It's just integrate the Bernoulli equation, and I get an expression which I can handle. So back to the FRAM, and here is my model vessel. It's a quadratic function in x1 and x2. So L is the length of the ship, and W is the width of the ship. And important, so when I do these computations, I play with this draft. This B naught is increased from a small value as far as I can until the model crashes. So I do this from I do the calculations from a small draft up to 1. So the upper layer depth is either 4 meters or 5 meters. Nansen didn't know exactly where it was. So here are some calculations with h naught equal to 5 meters. So here you get the nonlinear resistance coefficient versus a fluid number, and h naught is 5 meters. And this is this function CdW over B naught over h naught squared. As function of this B naught over h naught. So here it is 0.25, here it is 0.5, 0.7, 0.8, 0.9, and extrapolation to 1. But you see, as when you move from like fluid number 1 and reduce the fluid number, you have the common curve. But then, of course, the deeper the ship gets, the higher and higher you get up here. And on Friday, you will have a talk by Dr. Grue from Dalian. And she will actually talk about the peak reaching actually as far down as fluid number 0.5. Because she's doing experiments, and she can do the braking, I cannot do the braking. But then you see that as you increase the draft and decrease the fluid number, you have a very, very interesting steep slope at the small fluid numbers. So for fluid number around 1 and little less, the linear theory is actually doing quite well. But when you try to go down in the fluid number, linear theory is completely off. You need to do the full. You compute short waves and very, very strongly nonlinear effect. So here is now the nonlinear resistance coefficient as function of the draft of the ship. So you increase the draft of the ship, and then when you do this ratio here, it's almost like a linear function. But the smaller the fluid number gets, the more maybe troublesome it is. Yeah, and the linear theory for the small fluid numbers is simply giving about 0. So then we can also estimate or calculate the interfacial elevation. What is very similar to the iceberg case, which was measured by Morrison and Goldberg, is that you have a lift up at the rear side, very systematically. You have a little bit of depression in these subcritical fluid numbers. A little bit of depression ahead, but you have a very strong enhancement at the rear. So we have a suction. Some calculations with H with a more shallow pycnocline. So then these are actually calculations. The model didn't crash until well, it survived even 1, so it was touching the pycnocline. And then if I should do a prediction for FRAM, I need to do an extrapolation, which I'm doing here. So that is, of course, an assumption. But now if you merge all these resistance coefficients for B naught or for the draft of the ship equal to the pycnocline depth for 4 meters and 5 meters, you can see that the 5 meters curves are here. The linear is way up here, but the 4 meters are here. So you have like you're able to move the very steep hill to the small Froude number by this reduction of the pycnocline and this larger ship. So back to this curve, the empirical calculations of the dead water drag. Now I can add the calculations. So this is the calculations with 4 meters depth of the pycnocline with a draft corresponding to that level, and this is an extrapolation for the real draft of FRAM. So maybe this is not realistic, maybe it's somewhere in between, but you can see that at least here we get an estimate of the Froude number which FRAM was sailing at, the intersection between these curves. So we can say that FRAM was sailing at a Froude number of 0.55, plus minus some number which we cannot really decide. It corresponds to 1.1 knots and a speed reduction of 1 to 4.5. If the pycnocline was deeper, the Froude number is 0.06, or is 0.6, and the speed reduction factor is 1 over 3.6. If the pycnocline level was at 3 meters, what happens then is that these curves move down. These curves move up, and the Froude number gets smaller, about 0.5. So then the speed reduction factor is 1 over 5.7, larger than the original estimate. So we conclude regarding the drift or the speed of FRAM. We can conclude that the pycnocline in that situation was between 4 and 3 meters. But Nansen did not measure that quantity. So this is the conclusion of this particular investigation, which is taken down in a separate paper. So how is a wave wake at the small supercritical speeds? So here is a nonlinear interfacial elevation, eta over h naught, at Froude number 0.55. So you can see now the wave wake here. Here is a model of the ship. You can see it here. But you can see that the wave height is 1. So plus eta max minus eta min is the same as the upper layer depth. If the Froude number is 0.525, this is the wave wake. And if you do the linear, you get basically nothing. You get 10% of the nonlinear wave wake and no force. Force is 0. And here you can see the reason. The pressure below the ship is very symmetrical. So returning now to the iceberg case. The conclusion of my presentation is that the dead water resistance has a very steep slope at small subcritical speed for geometries of draft comparable to the pycnocline. And FRAM did not overcome this resistance hill. The calculated wave wake of FRAM has a wave height of approximately h0. So similarities with the icebergs. If a pycnocline exists in the sea at a depth comparable to the draft of the iceberg, then you would expect a great dead water resistance hill at small Froude number, much less than unity. The observations by Morrison and Goldberg showed that the internal wave height was comparable to h0 and Froude number approximately 0.6. So which is here. So Nansen said that the Froude number 0.555 and this iceberg says with a Froude number 0.6. So it's kind of very, very similar. The interface was uplifted at the backside of the iceberg, similar as in the calculations with the FRAM. So the main conclusion is that the dead water resistance at small subcritical speed with Froude number about 0.6, 0.5 provides a very considerable break on the motion of FRAM and the drift of an iceberg. And here are the references. And in these two works here, we cite all the work of Professor Milo and Tulin and so on. That the difference to this is that we discuss now the big increase of the resistance at the small subcritical Froude numbers. That's all. Thank you very much.
Yes. Just like to compare iceberg and FRAM, because in case of FRAM, you had fresh water on the surface of salt water, so therefore you had big difference in density. So then, if FRAM produce internal wave with amplitude about the thickness of upper layer, so then it could be greater. Of course, then resistance of ship, if it would be in water with constant density, because ship is well streamlined body, and mainly resistance is coming from weight resistance, and skin drag coefficient is very small. In case of iceberg has very bad shape, so therefore form drag is very big. So in addition, this top layer thickness is also very, very big. So then probably density gradient was much smaller than in case of FRAM. So therefore, I think that of course effect of dead water has place, but a portion of resistance coming from dead water effect in case of iceberg is still is smaller than main resistance coming as drag resistance as from form drag of iceberg. So then,
yeah, I think well, it's one thing we should be very which is very clear. Here I have an effect of 100.
Yeah.
So the skin friction, the frictional resistance,
yeah,
is 1% of the dead water resistance.
yeah,
And it was that for Nansen,
yeah,
because he encountered that big hill and he could not overcome the hill. I'm computing that hill for FRAM.
yeah.
And the hill, you can, I mean, it's no doubt, it's very clear. You have two sources of energy losses. One is the wave wake, and other is the local pressure. Of course, they are kind of mixed, but you can evaluate the energy loss in the wave wake, which is just the waves, regardless of how they are made. So that energy loss is there, independent of the processes how it was made. So that is very clear. You can have viscosity, you can have like flow separation. You would hear that in about that in the presentation by Dr. Grue on Friday, so you should come to her talk. But still you have the internal waves, which live their own lives once they are generated. And then, of course, the scale here. The FRAM ship was 30 meters. The pycnocline depth was between 3 and 4 meters, because I calculate that. It would have been very interesting to discuss that with Professor Nansen. I think he would be very keen. And it was fresh water above salt water. But the reference speed of the internal waves is the internal wave speed. So that also leaves, that is always, it's one reference. And that gives a Froude number. And the Froude number is universal. So you can do an experiment in a lab with a density jump of 1% or 1 per mil and 0 point, how many zeros you want, but you will always get the same Froude number. So that is the answer to that question. So of course you will have all these processes. You will have this relation here. This will now, instead of being extracted like this, the skin friction, you will have like some drag coefficient here and some drag coefficient here, but this guy here is just a function of the Froude number. It's a function of the waves you have made. And it can be the double of the other. In my case, it was 100, so it's a very pronounced effect. Doesn't matter. But, and then when you have, what you have here is this picture. You have a small, you go from a small Froude number and you increase the Froude number a little, and you encounter this it's a huge hill. You cannot overcome it because it's trying to make the waves much bigger than the thickness of the upper layer, and it's a tremendous break. Of course, the next step is to calculate it for that isolated iceberg. So I need to do maybe develop a new model because I can't calculate that. But you will find the same hill, and it's a very strong coincidence that the Froude number of Professor Nansen was 0.55, and the Froude number in the paper you gave me is 0.6. That's very close, and it's accounted the same hill. Yes.
Yeah, I'm fully actually interested in the mathematical solution, and for the problem that you showed. Can you say something about what happens if you actually have a submerged body? Say, because you showed a solution for a ship, right? But what if you have a submarine, for example, or a fully submerged body? In terms of the solution, how valid would it be?
I haven't done exactly that calculation, but that's of course fine.
It's completely.
Yeah.
So the other part of the question, in the case of the ship, for example, why not using slender body theory, which would make things?
I get very much different results from the slender body theory. You will need to read the papers. I discuss the relation with Professor Milo's work, Professor Thulin's work, and so on. So when you get out of the kind of the linear regime, then slender body theory is not maybe working so well. That's my recommendation. But in particular, in this, I had a long debate with Professor Thulin on this paper. I thought I was going to show some results of the nonlinearity. It actually then reduces the amplitude. The linear blows up. It's the opposite, because that is a supercritical. so here it compares the fully nonlinear compares nicely to observations, to experiments in a fjord, in an Arctic fjord. So you do want to read that paper. I can give it to you. So it's a very interesting discussion. So these waves are so huge, so slender body theory is not really doing a good job when you are outside of the kind of linear regime. But inside the linear regime, it's fine. But here, the interesting thing is to have bodies interacting like with the, or almost touching, or more than touching the pycnocline. Then you have this dramatic interaction, and then you have you need the fully nonlinear method. So in the supercritical case, why I can do that? Actually, I'm computing a very huge ship, which is intersecting with the pycnocline, but in the supercritical case, it pushes the pycnocline down, so I can my theory is valid. And it's a dramatic effect. Yeah, I had a very interesting discussion with Professor Tulin on this work because he was very critical and so on. And then I could identify where is it really needed a strongly nonlinear theory. So that is answered in that paper.
Please, yeah.
Very interesting talk, John. I'm not going to talk about the wave drag, but also I want to talk about the wave profile. According to the original paper by Nansen, you observe that, I mean, the Kelvin angle tend to open up to almost 90 degrees.
Yeah.
Here, I mean, it's still probably around the 19, 20 degrees, around the dead water conditions. So, I mean, how do you explain these discrepancies with the reports of Nansen?
This is actually what he wrote. This is right from his text. So now I really chase the original literature. And it's much more of it in Ekman. But this is what he wrote when he was on the ship. So there you can see, that is exactly what he wrote. And now the point is that Nansen was, I have been given talks in Norway about Nansen. So I know his science. He was very accurate. He was really a petimeter. He was doing things over and over again. So I can correct him. I can compute his Froude number. I cannot say it's more than accurate than plus minus some small digits. But it was 0.55. And I can compute the wake. So you see now the interface, you have some effect of the interfacial elevation on the same size of the ship here. And that is an elevation. No, yeah? That is an elevation, yes. This is the elevation. So you can see, this is what he saw. What you have here.
He even shows some plots, you know, in his original paper, 1904.
1904, that is different. Yeah, so I'm not talking about, yeah, so in Ekman, yeah.
Trying to show that
yeah.
this is a really normal to the ship. So
Yeah. You get normal to the ship when Froude number is 1. I could show a lot of computations about that. Of course, it's difference between linear calculation and nonlinear, but it's not really very much different when regards to the force. But of course, yeah, that's an interesting point. This is what I get at Froude number 0.55 and 0.52, which is sailed.
we can talk about it later. Anyway, interesting.
Small question, very last question. It's about nonlinearity. It's looking you calculated your nonlinear problem by iterations, and I have an idea that actually the second order theory would be enough to reproduce your nonlinear effects. No?
This is not second order.
Is it?
No, it's not second order.
You said it's a convergence is very quick.
Yeah.
Sometimes
This is, I have the series here. So the point is that I have one term, two terms, and I compute the next term.
Yeah.
And in the range, the next term is 0. So when that starts, but I truncate here.
How many terms you need?
So 2.
Yeah, this means
But it's many terms, yeah.
second order.
So no, it's not second order because I truncate and I iterate on those terms. So it's strongly nonlinear.
Okay, so it's another one. Okay, it's not just the second.
But I leave it open to take the next term and compute. You can, I mean, if you really start to want to explore nonlinearity and go down in Fridtjof, well, you can go on. Yes, of course.
Okay, thank you very much, John, and we have a